Section 2.2, limits and continuity, picks up where the last section took off. So in 2.2, we're going to talk about this new topic of a limit, okay? And limits are one of the three main topics of calculus. So this is kind of our first intro into an actual calculus topic, okay? So sometimes when a function does not exist at a certain point, we say the point x equals c, we still want to be able to talk about what's going on at that point, okay? So when the function doesn't exist there, we still want to be able to talk about what's going on, but you can't say that it actually equals a value because the function doesn't exist there, okay? And I like the examples that they use in this section, but I kind of want to talk about this in a different way a little bit first, okay? So let's take a look at this graph, all right? This should look like one of the graphs that we discussed in 2.1, okay? If you're looking at this graph, you'll see that, let's just say this point is A, okay? So let's say that we have a discontinuity at A because the function is not continuous there, right? So to talk about what the function equals at A, you can't say what the function equals at A because the function at A does not exist, right? So the function at point A does not exist. So this function is not continuous. But if we wanted to discuss what would happen at A if the function existed there and was continuous, that's what a limit is going to do. So if you look at this point, and let's say that this y value, just to keep it consistent, let's say that this y value would be b, okay? So as we're getting closer and closer and closer to the x value of A, this function is getting closer and closer and closer to what would be the y value of b. And it does the same thing from this side. So it's going towards or converging towards a y value of b. It's just that somebody at that exact value of A took a small chunk out of the graph, okay? So there's a chunk that was taken out of the graph. But if the function did exist at A, it should exist at a y value of b. That should be fairly obvious. So the way that they're going to write this, you can't say the function at A is anything, but you can say the limit, and that's LIM. They usually do a cursive L, so it's LIM as x approaches the value of A of the function. So the limit as x goes to A of this function would be the y value, which is b. So this function, when x goes to A, goes to b, okay? So it's a way that you can talk about what the value would be without having to say that the function exists there. And that's the whole concept of the limit. The limit at A, as the function approaches A, is b. It's what it goes toward, okay? So now we can look back at their examples that they're using down here and kind of talk through it a little bit easier, right? So they want you to analyze what's happening to the y value. Your answer will always be a y value. Answer will always be a y value. Okay, so your answer is always going to be in terms of y, okay? They want you to analyze what's happening to y as x approaches 3 from both sides of x equals 3. Okay, well, they didn't give you the actual coordinate axis, but that's okay. We know as we're approaching the 3 from the left, we're going to a y value of 5. As we're approaching the 3 from the right, we're going to a y value of 5. So we could say that the limit as x goes to 3 of the function goes to the y value of 5. And that's it. That's our analysis, okay? Let's take a look at example 2. For the function below, they want you to analyze what's happening to y as x goes to -4 from both sides, okay? Well, as we're going to -4 from the left side, we get closer to the y value of 2. As we're approaching -4 from the right side, we're getting closer to 2. So the limit as x goes to -4 of this function, both sides of the function approach the y value of 2, okay? And the part of the limits, for some reason, that seem to confuse everybody all the time is that you're looking at this value going, oh, but y equals 3 at -4, okay? But that's not what they're asking you. They're not asking you what is the function at -4, right? Because the function at -4 is 3. They're asking you, what is the function doing as it gets closer to -4? Well, as it gets closer to -4, it's going towards 2. It's just that whoever took a chunk out of the function moved that chunk up here, okay? So they took a chunk out of the function and moved it up there, but we don't care about this point when we're talking about limits. All we care about is what is it approaching. So don't let these points confuse you. They could have put the point here, they could have put the point here, they could have put the point anywhere else, and it does not matter. All that matters is what is it doing as it gets closer and closer to -4, okay? So hopefully you can keep that straight when you're looking at some of these other examples. All right, the last one like this says for the function below, analyze what's happening to the y value as x approaches 1 from both sides. Okay, so as we're approaching 1 from the left, the function is getting closer and closer and closer to the y value of -3. Okay, as we're approaching from the right, this function is getting closer and closer and closer to the y value of -5. Well, hopefully you understand that -3 and -5 are not the same value, okay? We also discussed the fact that it doesn't matter which one of these is filled in because it doesn't matter where the point is at x equals 1. We care what it's approaching. But since they aren't approaching the same thing, we can't say that the limit as x goes to 1 of the function is either of these things because they're two different things, right? So we can't say that. But we can talk about the limit from each side. So here's what that notation is going to look like. We're going to say the limit, let me write it down here. So the limit as x goes to 1, and from the left is going to be, it looks like it's in the exponent spot, and you're just going to put a little negative sign. So this says the limit as x goes to 1 from the left of the function, and that goes to -3, okay? We can do the same thing. The limit as x goes to 1. If we wanted to say from the right of the function, well, the left was the negative, so the right is going to be a positive as like an exponent. So as x goes to 1 from the right, this function goes to -5. Okay? So as x goes to 1 from the left, the function goes to -3. And as x goes to 1 from the right, the function goes to 5, or -5, excuse me, okay? If they wanted the limit in general, as it goes to 1 from both sides together, you would have to say that the limit as x goes to 1, notice there's not a negative or a plus, that means in general. So the limit as x goes to 1 in general of this function does not exist because the left and the right values don't go to the same place. Okay, so that brings us to this theorem down here, this general limit theorem. There's another example of the notation. So the left, the right, in general, right? This theorem is very important. The limit of a function only exists if the function from the left and the function from the right go to the same thing. That should be fairly obvious compared to what we were just looking at. This one, the limit did not exist because this one goes to -3, this one goes to -5. On the one we did previously, this one, we could say that the general limit existed because they went to the same place. And this one as well, they went to the same place, so we could say the general limit existed. But they only exist when the limit from the left and the limit from the right are the same. And that's what this theorem says. The left-hand limit must equal the right-hand limit for the limit to exist, okay? And that's one of the main properties of a limit that you need to know, okay? So that's where limits exist. We'll take a look at the next examples in the next video.